Welcome to our SSEP presentation. I'm Alec Lewis, and this is
Kai Turner.
And
Dustin Fields.
We hope you enjoy our presentation on the effects of microgravity on oxidation.
Our SSEP project aims to test the effects of microgravity on iron oxidation. By exposing the iron sample to water while in a microgravity environment, we hope to study the effects of microgravity in the formation of iron oxide. Upon the experiment's return to Earth, we will be conducting an extensive metallurgical study on the iron oxide that forms. We predict that the microgravity will affect on how the iron oxide develops. Through the process of our project, we came up with these questions that will be addressed by the end of the experiment. How does the microgravity environment affect the density of iron oxide crystals? Will the microgravity environment affect the rate at which the iron oxide forms? Does rust attach itself to the iron rod differently in a microgravity environment? Will the solidity of the rust crystals be affected by a microgravity environment?
Here are some applications for corrosion research in microgravity. The first is that the International Space Station is partly made of high-grade steel. Steel is an iron alloy, therefore it would be logical to study one of its base metals, iron. Having a better understanding of how microgravity could affect oxidation and corrosion will let us solve possible future issues in space travel. We hope to provide insight on oxidation and microgravity conditions to further the study of corrosion as a whole and the susceptibility of materials used in space travel.
What is oxidation? Oxidation is a reaction where an atom of some element loses an electron or electrons to an oxygen atom to form a bond, as shown in picture 2. This is why the reaction is called oxidation. The oxygen is decomposing the material into a more stable oxygenated compound. In the case of iron 3 oxide, the focus of our experiment, iron loses its 2 outermost valence electrons to 2 separate oxygen atoms. The oxygen atoms themselves then receive 2 electrons from 2 different iron atoms. The resulting chain of alternating oxygen and iron atoms produce the iron 3 oxide crystal, as shown in picture 1.
Experiment design and material handling requirements. In volume 1, on the left, we will have an iron rod that is 3.175 millimeters by 63.5 millimeters, low humidity air, and epoxy. In volume 2, on the right, we will have 2 milliliters of water and air. For our proposed timeline for crew interactions, at A equals 0, we will have the astronaut unclamp clamp 1 and shake gently for 30 seconds.
For our experiment design, the iron rod in preparation for the experiment, will be contained in a low moisture environment. This is to prevent iron oxide from forming prematurely on our iron sample. The rod will be mounted level inside the FME and will not be in contact with any of the side walls of the FME. We'll achieve this floating position by securing our iron rod using epoxy into one of the end cap stoppers, or the end cap stopper in volume 1. Having the iron rod suspended inside the FME as shown will allow for more even formation of rust. It will also help prevent our rust crystals from being damaged upon re-entry, as securing the rod will prevent it from bouncing around inside the FME, potentially disturbing the delicate iron oxide crystals. We will be using 3 FMEs during our experiment. All 3 FMEs will be identical in construction, and the reaction will be initiated at the same time for all. The first FME, FME 1, will be sent to the ISS and examined upon its return to Earth. The second FME, FME 2, will be our main ground truth experiment and will be examined alongside FME 1. Our third and final FME, FME 3, will be our secondary ground truth experiment. We realize that there is no way to terminate the corrosion reaction once it has begun. So to compensate, we will be examining and documenting the state of FME 3 on the day of reentry of FME 1. We will then use the documentation we will have gathered to account for the time FME 1 spends on the ground post-flight.
Our post-flight analysis will go as followed. We will first perform a visual examination and basic comparison between our flight sample and our ground truth samples as soon as we receive our flight sample. Then we will perform a microscopic inspection of a small sample of our rust. We will use various optical microscopes to further examine our samples 1 through 250 times magnifications. Finally, we will reach out to a local metallurgical lab to perform a cross-section of our samples. We will then gather additional information on the crystal structure and depth of rust penetration into our iron rod sample.
We would like to thank the following: our facilitators in administration, Zaola Goidi-Verto, Kathleen Fredette, Angie Naskovsa,
We'd also like to thank industry professional Tom Cousins, partner and funders CASIS and Subaru of America.
We'd also like to thank the school system iLEAD Consortium and Santa Clarita Valley International Charter School. Thank you for your time, and are there any questions?
Hi, I'm Laura from McAllen, Texas. I wanted to ask about how you might control for surface area between the ground truth experiments and the FME going to the ISS.
Are you referring to the samples that we are using?
I'm referring to the interaction between the water and the iron rod. So I would think that there would be a difference because of the effects of microgravity. I was wondering if you're going to agitate your ground truth experiment in some way to simulate that. Does that make sense?
Yeah, yes, it does. We have not planned on that currently, but that is definitely something we can take into consideration in the future. Thank you.
You.